So Mike Walsh, software engineer with Peterson, he's also a committer on the Fluo project, is going to talk to you about leveraging Fluo, using Fluo to incrementally update data that resides in Accumulo. So Mike.
Hi, I'm Mike Walsh. I'm a software engineer at Peterson Technologies and a committer on the project. My talk is using Fluo to incrementally process data in Accumulo. So at last year's Accumulo Summit, Keith Turner gave a talk about the underlying implementation and design of Fluo. Kind of talked about the how transactions work, how they actually store their data in Accumulo. So I didn't want to just repeat his slides or take his slides, even though it would have been really easy. So I kind of took a fresh look at it and kind of developed my own slides. And I wanted to more talk about how developers can use Fluo to create applications. Therefore, this talk will cover the types of problems that Fluo can solve. So just like what type of problems make sense for Fluo, how a typical Fluo application works. I'm going to step you through a Fluo application, some best practices and common pitfalls. Fluo is, I'm a big fan of Fluo, but like it has issues you got to watch out for while you're programming. You can't just write anything and expect it to run quickly. And then I'm going to finish with the current status and future direction of the project. The project's on GitHub. It's in active development. We have lots of issues and that can be worked on. So my hope after this presentation is that you'll consider using Fluo in the future, just to play around with it or even contribute back to the project. We're not production ready yet, but we're definitely ready for someone to kind of toy on their laptop and give us some feedback if you're interested. So I'd like to start with a problem that Fluo solves well. This is kind of so Fluo is based on Percolator, which was the Percolator paper which Google created, and this is kind of like in a similar vein of what Google created Percolator for. So imagine that you want to maintain all the inbound link counts for all the websites on the internet. The example graph on the left kind of shows this problem just for a few websites. The arrows are just links from one website to the other. So there's an arrow with a link from apache.org to github.com, and the inbound links are like the actual pointing to it. So like github.com has 3 inbound links, apache.org has 2, while Fluo has 0. So this graph of the internet produces the table on the right. So this is kind of what we want to, this table on the right is kind of what we want to maintain for all websites on the internet. And, but this problem is really hard for 2 reasons. One reason is that to determine the number of inbound links for a particular website, you're going to have to crawl every website that could point to it. The second reason is that these counts can change over time as sites add or remove links. Websites change, they go away. People change the website. There's constantly changing of these links on the internet. Therefore, if you want to keep your counts accurate, you got to be constantly crawling the web and updating this table. So one solution that I'm sure most people are familiar with is just batch processing. I'm using MapReduce. So a web crawler could kind of scan the internet and keep like a cache of websites it sees. And on the first visit of the crawler to a website, like all the links on that HTML could then be counted in some sense, and just like a +1 or a -1 could be written to a log. And the way it could work in some sense, if the crawler visits the website again and a link is missing, then the count for that site is decremented. So counts are incremented or decremented by adding the website URL and a +1 or -1 to a link count change log. So every 15 minutes or so, these counts can then be aggregated, and then maybe every hour, the counts could then be aggregated and joined with historical data using MapReduce to produce the latest counts. So another solution could be to use Fluo to count these links. With Fluo, the process gets a lot easier. So you're still kind of crawling the internet and comparing what you have in the cache versus what you're seeing now to kind of do a +1 or -1 to kind of change these counts. But rather than having to write it to a log and run MapReduce jobs, you can make an update to Fluo. And this is possible because Fluo supports transactions. So you can have like multiple crawlers running at the same time, kind of incrementing the same sites at the same time, and you're not going to have like counts are not going to become off, because if you have one site, I mean, if you have one crawler doing a +1 and another one doing -1, you could potentially corrupt your data. But there is one problem with this type of solution, is that, you know, for popular websites, if everyone's, you know, occasionally if they're updating at the same time, it's okay, a collision will occur, and one of the transactions will need to be repeated. But if it happens often, the crawlers can kind of slow down. Now, there's kind of ways around this. I'll kind of touch on this later, but this is just something you need to watch out for when you're writing Fluo applications. So I kind of mentioned, so I'm kind of introduce you to a third solution. I'm not exactly recommending this. I'm just kind of showing how batch processing and Fluo can complement each other, and they can kind of, for the same application, you can kind of use both. So with this, it's like so this kind of shows a distribution of websites on the internet and the number of inbound links. So there's some very popular websites like New York Times or GitHub where there's a lot of inbound links, and as the crawlers are crawling the web, they're going to all be trying to update these links. And then there's unpopular websites like Fluo.io, or just, you know, most of the websites on the internet, very few links to them. So what you could do in some sense is that you could update the unpopular websites using Fluo and the very popular websites using MapReduce. And the reasoning for this in some sense is like, you really don't probably care about the changes of the link counts in the next 5 minutes for these popular websites, while you probably do care about changes, like a very unpopular website becoming suddenly popular in the last 5 minutes. That could be like a indication of some relevant content or a new website. So that's kind of like how you could potentially use both. But like I said, there is ways to get around these collisions is possible. So, you know, you don't exactly have to do this, but my point is just that there's, you know, using Fluo isn't just abandoning everything else you've used in the past. So over the next few slides, I'm going to cover the basics of Fluo. Fluo provides cross-row transactions and snapshot isolation, which makes it safe to do concurrent updates. So you can have multiple clients or observers updating the same data at the same time. This allows for incremental processing of data. So data can be like, you can write observers that kind of trigger each other in some sense. And so, you know, it modifies a certain row, and then that triggers another observer. So you can kind of ingest data and have it slowly process over time, but kind of query that in real time. It's based on Google's Percolator paper. It was started as a side project by Keith Turner in 2013. I started about a year after that. The project was originally called Assistmas, but it was renamed to Fluo because Assistmas kind of looked like Accumulo when you looked at it quickly in code. And it is also kind of hard to pronounce, so we decided to change it. It has been tested using synthetic workloads, but it hasn't really been tested in production environments. And while we've had some good results while testing it using synthetic workloads, it's not exactly, you know, we haven't really encountered all the issues that you would in a real environment. So we're not really recommending it at this time for production environments. So I want to talk about how Fluo compares to Accumulo. So Fluo is an API built on top of Accumulo. It has its own API. It uses its own, it has its own kind of table structure, but it really, in some sense, stores its data in Accumulo. And the way Fluo is implemented is using conditional mutations for transactions. So you need to use Accumulo 1.6 in order to run Fluo. You can't use older versions of Accumulo. So Fluo has its own table structure. It's really similar to Accumulo, except it has no timestamp. And Fluo applications, while it's like its own, it's kind of like an API on top of Accumulo. It also has its own processes. There's like an oracle that allocates timestamps to the clients and the observers, and there's also workers that kind of run user code. So like you got to think about it with Fluo. There's like a client front end that you can run from your own processes, and then these observers that you can run in workers that kind of Fluo runs for you. And these observers kind of look at the tables and run your code when changes occur to columns. So this slide shows the architecture diagram of how Fluo runs on a cluster. To the right's the cluster, and the left is like a client, user code. It'd be like web services or crawlers. So Fluo, it runs as we made a design decision to run Fluo within Yarn. Basically, because we require Accumulo, you need to have Hadoop available. So like, Yarn's already going to be there. And that kind of makes it easy. You don't have to like deploy the Fluo distribution to all servers on your cluster. You can just start up a Yarn application. And that kind of allows for some interesting things, like you could start a different number of workers for an application very easily and not have to worry about configuring multiple machines. And that kind of shows in here like how there's one of these applications has 2 workers, one of them only has 1. Workers can have multiple different observers. One thing to note here though is that like each Fluo application uses its own table. So in some sense, Fluo applications kind of have their own data sets. You kind of want to like, it'd be maybe a different group or a different team kind of working on different applications, but because we use different applications, people can share the cluster in some sense. And they can upgrade applications on their own, follow their own cycle. If they're ingesting a bunch of data, they can kind of spin up the application with a lot of workers, then kind of, stop it. So there's a lot of benefits to having this multi-application structure in Fluo. So there's 2 ways of writing, of interacting with the application. One's from the client, and then the other is from the observer. That's pretty much it, this slide. So here's some example client code. Pretty much what's going on here is that there's a document being added to Fluo. So the client creates a transaction that's kind of gets wrapped in this type layer. And the client then, it checks to see if the content column exists for the doc ID. If it doesn't exist, then it mutates the doc ID row in the content column. It sets the content, and then it commits the transaction. The transactions are done within a try statement to kind of close them at the end. So here's an example of an observer. So pretty much you like extend an observer class, and you implement this process method, which will provide you with a transaction and also the row and column that are modified whenever like a certain. So you kind of set at the bottom there. There's a get observed column, and you kind of set which column you want to watch, and then whenever that column is changed, like this process method will be called, and with the row and column that was changed. So you're given a transaction, which you can perform, processing during that. So you could, if a document was set and the content column, you could kind of parse the document in this process method, and then you could, perform. You could also read other rows in the table, and then you could kind of write your results to multiple rows in some sense. Because the advantage of Fluo is that you can do cross-row in some sense, and cross-row transactions. And then one of the advantages of doing things in observers is that if this transaction fails in the process method, it's just going to be retried. And observers can workers can kind of run, mini observers. They can kind of run in a multi-threaded environment, and it can kind of like churn through a ton of data. Therefore, like while you can kind of choose where to put your logic between the client and the observer, it's better in some sense to put most of your logic in the observer. that's kind of like a best practice. So I'm going to step you through an example Fluo application. I'm sure everyone here has done a word count application, but this one's going to be a little bit different in some sense, where I'm going to maintain the word and document counts as documents are added or deleted from Fluo in real time. So my application is kind of split into like a client and two observers. The client will add a document to the table and also mark the document for deletion. And then the observers are going to there's going to be one observer that's going to increase word and document counts when that document's added to the table. And then there's going to be another observer that's going to delete counts whenever that mark document for deletion is made by the client. So first, the Fluo client will add doc1 with in the column doc to the table. And the document's simple, it just says my first hello world. So this kind of shows the separation between the client side and the cluster. So when this occurs, the add observer is watching the doc column, and its process method is called with a transaction, and then it can then read the value of the document. It parses the words in the document and does a basic count of each word, and then it can then set word counts at each, for first, hello, it sets each of those, and then it can also set a total docs count. And this can all be done in a single transaction. That if one of these is not set correctly, it's going to fail. So this kind of shows what happens when a second document's added. So in some sense, the add observer is not just adding ones, it's actually incrementing the counts. It could increment it by 5 if it wanted to. Finally, or not finally, the Fluo client then marks doc1 for deletion. And then there's a delete observer that then sees that. It then parses the document again. It looks up the document, finds the words in the document, and then decrements counts for that document. So one thing you should notice here is that in every time the observer runs, it's actually going to modify the total doc row. This is kind of another potential collision area, because if two observers are kind of running at the same time, they're going to mark that row. So one kind of way to get around that would be to partition that total doc row by total doc A for all documents that start with doc ID A. You can kind of do that for A through Z. If all your doc IDs were only use letters, then you kind of partition the total document and then kind of sum it at the end whenever you wanted to return it. That would kind of reduce the collisions. So you just got to watch out when you're developing an application that you don't have that occurrence where everything's changed. Sometimes that might be okay if it's not a heavily used if the application doesn't have a ton of transactions. But if it does, you just want to avoid that updating it every time. So here's some things to watch out for when developing Fluo applications. So one is what I've talked about a decent amount is collisions. They pretty much occur when two transactions update the same date at the same time. Only one will succeed and the others will need to be retried. Some are okay, but too many can slow down the computation. So, and then you can avoid them by not updating the same row column at every transaction. So another thing to watch out for, which I haven't touched on, is write skew. And this is a little tricky, so if you don't get it, it took me a while to get it. It occurs when two transactions read an overlapping data set and make updates without seeing the other update. And it's pretty much the result is different than if the transactions were serialized, or one after the other. And the only way to prevent write skew is by making transactions update the same row column. So it's in some sense you want to force a collision, because if they're concurrent, a collision will be forced, and then only one of them will succeed. So one of the things you kind of run into is whenever you get introduced to something new is it's how does this fit with what are all the other tools out there? And so I kind of created this slide this is not the only major difference between these different tools, but it does highlight, I think, one of the major, to me, in some sense, is the difference between like, batch processing, MapReduce and Spark, incremental processing, Fluo and Percolator, and stream processing, which an example tool is Storm. So on this graph, like it kind of shows how some tools are good for like large join throughput, joining a small data set with a large data set. Some tools are good for processing latency. Some are faster, can work through processing data, get your result faster. So this graph kind of shows how Storm and stream processing they have very fast processing latency, and batch processing is very good with joining data, large data sets, and Fluo kind of fits in the middle. So in some sense, there's certain types of problems where like you want to use Fluo over batch. It kind of depends on your problem, and so kind of both cases, Fluo, you could consider Fluo to solve your problem. So I kind of stepped through some of the situations where you shouldn't use Fluo. You don't want to use Fluo to do ad hoc analysis on your data. Fluo applications, they take a lot of time to write. They're not really meant for like, a quick and dirty, trying to solve the answer to this problem. For these types of things, you should use like batch processing, Pig, Spark. You also shouldn't use Fluo if your incoming data is being joined with a small data set. In this case, like Storm's probably would be better. It'll be faster. The code might be simpler to write. So you should use Fluo if you want to maintain like a large scale computation using a series of updates, or if like your periodic batch processing jobs are taking too long to join with existing data. So here's a typical Fluo application lifecycle that we've kind of found works. When you're building a Fluo application, you want to seed the computation. You want to use batch processing to kind of seed the initial computation with historical data. So you want to in some sense, write a MapReduce job that does the computation and then loads that data into Fluo. Because while you could replay all your data through Fluo, so you could create a Fluo application and just kind of replay all the historical data and you would have the same result. But we've kind of found that in some sense, if you're doing a huge computation, a year or a couple months, you want to just run that through, use MapReduce to create the initial result, and then seed your Fluo table. And then you should use Fluo to kind of process new data as it arrives. So as data arrives every 15 minutes or even in real time, you can then have that data run through your Fluo application. And so what's nice about Fluo is that while all that's processing, you can query Fluo and notifications can be made to users. So that's kind of like a benefit over in some sense batch processing, is that you can kind of have access to the current state of the cluster while the whole computation is going on. So in the next couple slides, I want to talk about the current status and future direction of the project. The slide shows the major progress that we've made. So this kind of give you a starting point. Google released its Percolator paper in 2010. So it took about 3 years, but then Keith started working on the Percolator implementation for Accumulo as a side project. So Fluo was originally called Assistmus. He did a lot of the core implementation in that first year. And by the end of 2013, Fluo could kind of process transactions. But not a lot of applications that had been written. It just was, it didn't have a really set apart API at all. So when I joined in 2014, Keith's kind of been splitting his time between Accumulo and Fluo. I was able to focus, and we were able to get a decent amount of work done by creating a stress test so that we could kind of test Fluo and kind of push the limits of it. We solidified the client observer API. We did the name change, which was a decent amount of code that was changed for that. And we've been working, and we worked on running Fluos, Oracles, and Workers in Yarn. Towards the end of last year, we released the 1.0 alpha, and that's the current stable version right now. We should be releasing a 1.0 beta very soon in the next couple of weeks. And then, in the past couple months, we've been kind of automating being able to run a Fluo cluster on Amazon EC2, and we just added some multi-application support. So I talked about this in the previous slide, but kind of want to go in depth about the Fluo stress test. It's kind of important because this is kind of how we're going to be finding a lot of bugs and kind of solidifying Fluo. What's tricky about a Fluo application is that you can't get it wrong, because if these transactions start to run concurrently and corrupt each other's data, or the result isn't the same as if you ran a MapReduce job, it needs to be solid every time. So we kind of created this test to kind of cause a lot of collisions and kind of stress Fluo at scale, but we wanted to be able to easily verify it. So the way the test works in some sense is that you're building this bitwise try. You're adding random integers, and here's just the bits at the very bottom, to the bottom of a try, and then we have observers that kind of see the addition of these integers, and then kind of percolate these counts up to the try. So you see at the bottom row, there's 5 random integers, and then the observers kind of work through and then percolate the count up to the top, which shows 5. So in some sense, you can ingest as many random integers as you want, and then at the very end, you can kind of verify the result. And we've also kind of created a MapReduce job that kind of runs separately and also verifies the result too. So we really know if Fluo was kind of running correctly. So we've kind of run this a lot of times. We have found some bugs, but it has been pretty successful with getting the correct counts at every time. So another thing we've done in the past year is make it very easy to run Fluo. We kind of put this in a separate repo, but there's this repo called Fluo Dev, and it allows you to run Fluo easily on your local machine. One of the problems with Fluo is it's great because it's we don't want to reuse things, but we're dependent upon Accumulo and Hadoop and Zookeeper. So if you want to get started really quickly, you can't just, you have to set up all these dependencies. But with Fluo Dev, you can kind of clone Fluo Dev, you can do some basic configuration steps, and then you kind of have this Fluo Dev tool, this command line tool, where it can downloads Accumulo, Hadoop, and Zookeeper tarballs. You just run the setup command, and it sets them up locally. You can then use all the monitoring pages. You can then run Fluo Dev deploy, and that'll build. You point towards your Fluo repo. It builds Fluo and deploys it, so it will work with that Accumulo setup that you just created. And then now you can after this point, now you can kind of use the standard Fluo commands that you would run in a production environment if you already had everything set up. So then there's this Fluo script that you can then run Fluo new, which kind of creates some base configuration for your app. You can then modify the configuration, and then when you run Fluo init, it initializes the app into Zookeeper. And that's kind of where we store state for Fluo. So you can stop and start apps, and they all their basic state is stored in Zookeeper. So there's a start command for the Fluo command, and then there's also its own scan command, because while you can scan an Accumulo table, while Fluo stores its data in Accumulo, if you were go to scan an Accumulo table, you would see the data, but it would be mixed in with all this underlying data to handle the two-phase commits and the underlying transactions. So we have Fluo Dev for running locally on your own developer laptop, but we also have another project called Fluo Deploy that makes it pretty much just as easy to run a Fluo cluster on Amazon EC2 with a configurable number of nodes. So this kind of brings me to the whole ecosystem that we've created in the last year. One reason for this was that we didn't want to have this giant code base that had to be maintained with, we didn't want Fluo to be some giant code base. So we kind of split off things that kind of made sense. So they can kind of be developed on their own. I kind of mentioned Fluo Deploy and Fluo Dev. We have 2 example applications. There's a quick start, which is a really simple example. I think it's just a word count. And then there's the phrase count example, which is a little more in depth. We also have like a repo with our project website. So, theoretically, anybody could submit a contribution for a blog post or documentation changes. Fluo Stress was kind of made its own repo. It was initially in Fluo, but then it was pulled out because the thought would be, we can kind of iterate on stress and then maybe run it against older versions and not have to like be bound to a certain version of stress with a certain version of Fluo. So I wanted to talk about like the future direction for the Fluo project. Basically our primary focus, we're going to be releasing a beta soon, but at 1.0 it's going to be, Fluo should be production ready. I don't know exactly when that will be. It'll be kind of dependent upon, when we no longer encountering bugs that we think are going to really, cause people pain when running in production. So that's kind of like our main focus. At 1.0 our API will be stable. So at that point, even though I think the API is very stable right now, it shouldn't change that much, but at 1.0 we do have a guarantee that it will stay. You should be any application you write should work through any 1.1 or 1.2 release. Kind of lists some other possible work that we might work on. So we have this try stress test that kind of uses synthetic data. It'd be nice to kind of create like a real world application that kind of shows Fluo using like real live data and kind of works through some of those problems. One thought was just to use some common crawl data because it kind of fits with the whole crawling the web and it's a really interesting data set for Fluo. Another possible thing we might work on is while using Java for Fluo has been great, given it uses Accumulo. We'd like to be able to like maybe use Python for writing observers. This might provide some good abstraction and make it easier for people to write observers. We also want to look at running Fluo on Mesos. While we definitely want to keep the Yarn support, we just don't. I'm definitely excited about having Mesos and Yarn out, and we just want to be able to depending on where you're running, it doesn't really. If you're using Mesos, you can use Fluo. We don't really want to be. We want to be like agnostic when it comes to that. And then another possible issue or feature we'd like to work on is it would be auto scaling up and down Fluo workers based on the workload. So like what typically happens is like you might have a constant stream of data going into your Fluo application, but you could potentially have like a surges where you want to like scale up the workers to handle it, to process all the transactions, to work through it. Other times then you might want to scale it down to give those resources on the cluster to other people. And this is kind of where the benefit of running in Yarn is that it's going to be very easy to like do this on a cluster. You don't have to like kill processes or anything like that. So we'd like to be able to do some sort of auto scaling based off of like maybe the number of notifications that observers have to process. So if you're interested, definitely get involved with Fluo. Feel free to experiment with it. The API has stable, but we don't have a commitment. We're not going to make a commitment to 1.0. The tools and development process have gotten a lot easier recently, so it should be fast for you to get up and running kind of quickly. But it's not recommended for production yet. And if you're interested, we're definitely open for contributions. I mentioned some of the larger issues, but we have a lot of small issues that are open on GitHub. And we follow, this is the first time I've done this, but we followed a review then commit process, which is actually great. Like Keith, Corey, and I are committers, but anybody, even us, all commits kind of go through a review process where you submit a pull request, and so everybody kind of comments on the commits, and they kind of, we've definitely like made a lot of, we've caught a lot of bugs before it kind of has become an issue. And like small, easy commits, they really haven't been a problem to review. It's pretty fast. So I've definitely been a big fan of doing that. So that's pretty much it. If anybody has any questions. Yeah. Yeah, so Keith mentioned, I think he probably mentioned that in his last talk, which actually would be good to review. We kind of took a different approach. But so the best way, it kind of depends. Like you can scan, you can, your client can create a snapshot and scan the table, but it could potentially slow down. So if you really care about speed, it's not that you can't read from a Fluo table, but if you really, really care about how fast your reads are, you should export the data. And exporting, it doesn't have to be to Accumulo. It could be to like Elasticsearch or Solr or even a MySQL table. Well, we haven't really experimented that much with that because we've been focused on just kind of building the infrastructure of it. Yeah, there's totally a way to export your data. How are the observers what? Oh, well, so they don't run on tablet servers, so they're not implemented by iterators. It's kind of, they run in their own process, which are worker processes. So it's completely set. Is the concept similar to, I mean, it's similar in some sense where it's like your code is running in an external application. It's not running in your own user process, but they don't use iterators to implement. They have their own thread pool, and they pretty much like scan for notifications in a certain locality group and then process that transaction. Yeah, it's just your table kind of, it's like you're expecting the state to be a certain way in one data set, and so you're reading and kind of making a decision off that, but someone else is reading. It's like, it's just kind of it causes like a kind of like a corruption, but it's not in Fluo's sense. It's more like your own. You're not reading things in time in some sense. So in some sense, if you want to make sure that something's written before something else, you want to actually update the same row, so they have to happen serially in some sense. Yeah.